In this lesson, we're really focused on one thing, finding the inverse of a matrix. But that also presupposes that it exists, because not all matrices will have inverses. So we will have to explore a little bit about the conditions under which we do have an invertible matrix. But first, I'm going to just start out with a little bit of motivation. Let's grab something that we know to be true, that 3x equals 6, and if we divide both sides by 3, then we end up with x being equal to 2. It's a very simple process, but it involves division. So if we were in the similar situation in matrix world, where we had ax equals b, and we wanted to solve this, what we would like to be able to do is divide both sides by the matrix A. Unfortunately, there's no such thing as division of matrices. But the good news is that when we do division, there's actually an inverse process. So the inverse process involves multiplication. So we can take 1/3, which is the inverse of 3, times 3, and multiply 1/3 on both sides, and end up with the same result. Because 3 times 1/3 is 1, times x equals 2, and of course 1 times x is x. Not really all that profound, but the idea that 1/3 times 3 is equal to 1 actually does have some relevance to us here, because it turns into what's called the multiplicative identity. The one element in the world of numbers is what we would refer to as that multiplicative identity. And in the world of matrices, we also have that multiplicative identity. We introduced this in an earlier lesson, and it was called I. So if I take I times any matrix, I get that matrix back. So we notate the inverse of a matrix with a superscript to the -1. So if A is invertible, and we'll use a capital letter A instead of a lowercase a here, then the inverse of A is notated by A inverse. Again, assuming that it exists. We'll talk about the existence part of this in a little bit. And if we allow ourselves to use that notation, we can take our expression ax equals b, and now we can multiply both sides by A inverse. And you'll remember, multiplication is not commutative, so we have to be careful. If I multiply on the left side over here with A inverse, I have to multiply on the left side of the other side of the equation for A inverse as well. So our statement becomes A inverse A, or times A, times x equals A inverse times the column matrix B. A inverse times A is equal to the identity matrix, just like 1/3 times 3 is equal to 1. So times x equals A inverse times B. And any matrix times I is that matrix again. So we have x being equal to A inverse times B. So it's really just trying to provide some motivation for why we're interested in inverse matrices. There's other reasons why as well, but this gives us some familiar motivation for solving algebraic type situations. You could even imagine that you might have equations like ax plus c equals b, and maybe we would want to solve that out again. We could subtract the matrix C from both sides, just like we would algebraically. But again, in order to deal with the product of A times X, we've got to use the inverse. Again, that's assuming that the inverse actually exists. So now I think we've got a little bit of motivation. So let's see if we can figure out how to compute the inverse of a matrix. And it all kind of hinges around the idea that if I multiply a matrix times its inverse, I get to I. So for matrix world, we need a matrix B such that A times B gets us back to that identity matrix, and then this matrix B would then be A inverse. So let's work through an example, and this is really meant to illustrate and motivate how we go about finding that inverse. It's not initially how we would do it anyway, but this again is to provide that motivation and understanding for where the process comes from. So let's take A to be equal to the following 2 by 2 matrix, 1, 2, 3, 5. And again, we want a matrix B that we don't know, and I'll just use A, B, C, and D to represent what numbers are going to be in there. We don't know what that is, but we want to multiply those two matrices together and get the identity matrix I. So A, B, C, D. And after we do that multiplication, we want the 2 by 2 identity that looks like this. So here's our setup for how we would initially think about trying to find that inverse. And we'll use some information that we've developed earlier so we can express B and I in column form. And we have so this is our alternative definition of multiplication. A times B1, B2 equals E1, E2. So this is just looking at the matrix A, and then we're calling this matrix B, and then this is I. But within I, you have E1 and E2, and this is going to be B1 and B2. So we're taking A times the column B1, and then A times the column B2, and over on the right-hand side of the equation, you can see I've got column E1 and column E2 associated with each of the columns in I. So just trying to articulate where all those pieces are coming from there. And we can take this a step further and say, or if we write out some of this stuff, I get 1, 2, 3, 5. That's my matrix A, times B1, which is AC, and that's going to be equal to E1, which is 1, 0. So extracting that out of our statement here. And there's another piece to this, which is A times B2. So 1, 2, 3, 5 times the column B2, which is BD, and that is equal to E2, 0, 1. So again, extracting that out as well. So now, if we were to solve these out, essentially you end up with a system of 2 equations and 2 unknowns here, and a system of 2 equations and 2 unknowns here. Now, the row operations for solving each of these are going to be equivalent because the matrix A is the same for both of them. So what we can do then is just put them together into one single augmented matrix and simultaneously solve for AC and BD in the following way. So 1, 2, 3, 5, and we augment our matrix, and we can put the solution that we're hoping for, which is 1, 0, and the second solution we're hoping for, which is 0, 1, this way. So I'm going to simultaneously solve both equations. If we were to get rid of this for a minute, then we're solving for B and D. And if we were to imagine that we didn't have this as part of our augmented matrix, then we'd be solving for A and C. Again, the row operations are the same, so we can solve for them simultaneously this way. So at this point, you just put the thing into maybe Octave, hit row ref for that particular matrix, and what we end up with then is 1, 0, 0, 1 on the left-hand side, and minus 5, 2, 3, negative 1 on the right-hand side. And then we get what we want. This is going to end up being A and C, and this is end up being B and D. So that means that B is equal to A inverse, which is equal to negative 5, 2, and 3, negative 1. So in reality, when we ask to find an inverse for a particular matrix, we generally just jump right to this statement where we have the matrix A on this side and the identity matrix of the same size on the other side. We row ref it, and then we look at the left-hand side here to determine what the inverse matrix is. That takes care of how we can do it. And even if it was a larger matrix, like a 3 by 3 matrix or a 4 by 4 matrix for A, we would still solve it the same way. We set up matrix A, I, row ref it, and then look over here for what the inverse is going to be. So that gets us a sense for how we can go about solving for an inverse. Next question would be, when does it actually exist? So let's deal with the existence part of this now. And there's really not a whole lot that has to happen. We just have a couple of conditions. One, A must be square. And using a definition from our lesson prior, A must be non-singular. So what does that second statement mean again? If A is non-singular, it means that the only solution to the homogeneous system is the trivial solution. So that means the column vectors of A must be linearly independent in order for A inverse to be even possible. So those are the only two conditions that we actually have to verify. And we know how to do both of those. One, visually, we can see pretty quickly whether or not it's square. And two, we just have to test for non-singularity. The reality is, if we're doing this on a computer system, the test for singularity is going to pop up in the same context as trying to solve out this kind of a problem. You're really just observing whether or not this side turns into I, the left-hand side here. If this turns into anything other than the identity matrix, then A was singular, and then the inverse doesn't exist. So in practice, we can just throw the thing into our form, row ref it, and if it works, it works. If it doesn't, then we'll find that out at that particular point. We don't have to take any additional steps there. There's one other thing that I'll point out, and that is that there's a bit of a shortcut for a 2 by 2, and this can be handy to know. So here it is. We'll take A to be just a generic matrix, A, B, C, D. Then A inverse, again, if it exists, is equal to 1 over the determinant of A. And I know we haven't talked about determinants, but that's okay. And then it's times D, negative B, negative C, and A. So what we do on the shortcut is you're going to flip positions on the main diagonal. You'll see we go A, D, and then when we flip them, it's DA. And then we negate the values on the off diagonal here. We then have to multiply by 1 over the determinant of A. Again, I know we haven't talked about what determinants are, but we will soon talk about those, so it's worth at least noting that this is what you're going to do. The determinant itself is pretty easy to compute for A. I'll just write it down for you. The determinant of A is equal to A times D minus B times C. So it's the product here minus the product here, and that's the determinant. Again, we'll talk about that more in detail in a little bit, but for now, at least you know that shortcut, which I think is kind of useful for a 2x2 matrix. Back over version 2 of the properties of matrices. So there's some additional properties that we want to note around inverses. So take a look at that handout, and also look at the version 2 of basic equivalences, which essentially amounts to theorem 18. So just take a look at those two things. I'll put some links in the lesson for you so you can review those and have those handy for you. But make sure you're familiar with the particular properties surrounding inverses as well.